So welcome everyone. It's a pleasure for me to introduce you to our speaker today. This is Mariel Supina from University of California, Berkeley. And she's going to be talking in the preseminar a little bit about the universal valuation of Coxeter matroids.
Yeah, thank you. Thank you for inviting me. So the universal valuation of Coxeter matroids is the title of like the work that I'm presenting in the seminar. And so then right now in the pre-seminar, I'm just going to talk about some like different families of polytopes that will come up in my talk. And also a little bit about like what a valuation is. So first of all, everything, well, my screen just went black for a second. I hope that, okay, anyway, so everything will always be living in some vector space V. And so then we say that a subset P is a polytope if it satisfies one of these two things. Either it's a bounded intersection of finitely many closed affine half spaces. As you can see on the left picture, we have this pentagon, which is the intersection of these. Basically, for each of these 5 lines, I tell you which side of the line I want to be on. And that gives me 5 different half spaces. And then when I intersect them, I get this pentagon. And alternatively, we could define it in terms of the vertices. So I can give you these 5 points on the right picture, and then I can taking the convex whole means that I'm taking the smallest convex set containing all of those points. And so that gives me the same pentagon. So these are 2 different ways to characterize polytopes. And these are kind of the basic objects that I'll be working with. And I'll also be talking about polyhedra more generally, which is sort of a more general thing where now I don't require it to be bounded anymore. So if I take the first bullet point and I remove the word bounded, then I get the definition of polyhedra. So like, for example, if I just took a line and I just told you what side of it I wanted to be on, that would give me a half space, which is also a polyhedron, but not a polytope because it's not bounded. Okay, so the sort of main algebraic objects that I'll be talking about in my talk are called valuations. So I want to tell you what these are, and in order to define these, I have to tell you about subdivisions. So there will always be some family of polyhedra that I'm working with. So it could just be all polyhedra, or it could be more specifically like generalized permutahedra or matroids, and these are things I'll define later. So if I have some family, script P, then I'm going to say that a subdivision of a polyhedron P in my family is a set Q1 through QK of other polyhedra in my family satisfying these conditions. So basically, they just need to only use vertices that were already vertices of P, and their union needs to give me P. And if I take the intersection of any 2 of them, I should get a proper face of both of them. So for example, if my family is all polyhedra in R2 and my P is the square, then I can take these 2 triangles Q1 and Q2, and you can see that their union gives me P and they only use vertices from P. And if I intersect them, I get this diagonal edge. So that's a face of both of them. And so this is one subdivision of P. Subdivisions end up coming up a lot, both in like discrete geometry, but also in like algebraic geometry and tropical geometry. And this is kind of why people are interested in valuations. And that's because valuations are the functions that behave nicely with respect to subdivisions of polyhedra. So I'm going to give 2 different definitions of valuations. And so here's the first one. The first one's more geometric, and then later I'll give a more algebraic definition. So we say that a function f that takes in polyhedra in the family and outputs some values in some abelian group, we say that it's valuative if basically I can evaluate f on a polyhedron by subdividing the polyhedron doing inclusion, exclude, or sorry, subdividing the polyhedron, evaluating F on all the faces of the subdivision, and then like doing inclusion, exclusion on those faces. So here in this formula, when I have a subset I of the indices 1 through K, that's just going to mean I'm taking the intersection of all the QIs where I is in that subset. It turns out that a lot of functions on different families of polytopes that people like to study have this property of being valuative. So one example that's not too hard to see is Euclidean volume of polytopes. And this one we can see just because the volume of anything that's not full dimensional will be 0. And so this is just saying it's valuative just means I'm saying that I can sort of subdivide my polytope and I can compute the volume of all the cells in the subdivision and add them up and get the volume of the whole thing. But it turns out that Ehrhart polynomials of lattice polytopes, Tup polynomials of matroids, order polynomials of posets, and Chow classes of generalized permutahedra, and many, many other things also have this nice property. And so this is kind of the motivation behind studying valuations, and in particular, trying to find a universal one that I can get other valuations from. So this is kind of, I think this definition of valuation gives some sort of geometric intuition for why people might want to study it. But I'm actually going to be, like, all the work that I am going to talk about was using this other definition that I'm about to show you. So this one on this slide is also called the weak valuative property, I think. And now the one I'm about to tell you is called the strong valuative property. And technically they're not always the same, but on the families that I'm interested in, it turns out that they do happen to be the same. And so I guess I want you to think about the one I just told you for the intuition, but really I'm going to be using this definition for like the work that I did. And so an alternative way to define a valuation is to say that if I have some polyhedron, I can get its indicator function, and that's just going to be the function that takes in a vector in the vector space, and it outputs 1 if that vector is in the polyhedron and 0 otherwise. And then I can, once I have the indicator functions of all the polyhedra in my family, I can take all of the finite integer linear combinations of these, or in other words, the Z module generated by these, and I'm calling that I of the family P. And I'll call that the indicator module. And so the alternative definition of a valuation is that it's a function from the family of polyhedra to an abelian group that factors linearly through the indicator module. So a function is valuative if there exists a Z-linear map F tilde such that F evaluated on a polyhedron is equal to F tilde evaluated on the indicator function. And I'll talk about this a bit more in detail in the actual talk, but sort of the intuition you can have here is that this indicator module kind of models the valuative property from the previous slide, because it has this kind of inclusion exclusion property built in, where if I take the indicator function of P plus the indicator function of Q, then I get the same function as if I took the indicator function of their union plus the indicator function of their intersection. And we can see that because, for example, on the left-hand side, that function, that sum of functions will be it'll be 2 if X is in both P and Q, 1 if X is in P or Q, but not both, and 0 if it's not in either of them. And you can check that that's the same function as the right-hand side. So this relation on the indicator module kind of should give some intuition as to why this definition, this algebraic definition, would be related at all to the one from the previous slide that uses inclusion exclusion on the faces. Are there any questions so far? Okay, so I'll go on. So that's kind of the first part. I wanted to define what a valuation is. And now I want to switch gears and tell you about some of the families of polytopes that I'll be talking about in my talk.
So Mariel, so I have a question.
Yeah.
So you mentioned commutative diagram. What
Yes, sorry. I took this slide out of the like other part of the talk, and in that part I am gonna have a commutative diagram. I just didn't have it in this part. Yeah, sorry. But if you stay, yeah, then you can see the commutative diagram later. Yeah. But basically it's just we can see that like we can say that like a function, a valuative function on the family is basically the same as having a z-linear function on this indicator module. So yeah. Okay, so now I want to talk about some families of polyhedra. So for much of my talk, I'll be talking about the case where my family is the family of deformations of some special polytope Q. And so we say that, so if I have some special polytope Q, we say that a polyhedron P is a deformation of Q if the normal fan of P coarses a subfan of the normal fan of Q. So if you know about normal fans of polytopes, you can think of this definition. And if you aren't familiar with this, then alternatively, you can think of taking the facets of Q, the codimension 1 faces, and sliding them along their normals, and that gives you a deformation. So for example, here, if Q is this hexagon, then I can take this like upper right edge and I can translate it out along its normal vector until it's gone, basically. And this just amounts to taking the supporting hyperplane from that hyperplane description that I said on the first slide, and I'm sort of moving the position of the supporting hyperplane, but I'm not changing the like orientation of it. And so if I slide this out all the way, then I get until this isn't like an edge anymore, then I get this pentagon P1. So that's going to be 1 deformation of Q. I can also, alternatively, I can take like Q and I can take all those sort of left and lower faces, and I can like take turns sliding them out as far as I can, and eventually I'll be able to slide some of them out forever, and I'll get this unbounded cone P2, and that's another deformation of Q. So the deformations that I'm going to talk about don't need to be bounded. They can be unbounded like this cone. So this is a general definition of deformations, and we call the family of deformations of Q, we call that def Q. But in particular, I'll be interested when Q is this very special polytope called the permutahedron, because then the family of deformations is what we call generalized permutahedra. So the permutahedron, so if I fix some positive integer n, then the n permutahedron will be the convex hull of the permutations of the point 1, 2, up to n in Rn. So for example, if n is 3, then I get the 6 different permutations of the point 1, 2, 3. And then that gives me the vertices of my polytope. I take the convex hull and I get this hexagon, this orange hexagon on the left. And if I go up a dimension and I have n equals 4, then I'll get this green polytope on the right, which has 24 vertices, or 4 factorial, the number of permutations of 1, 2, 3, 4. So one thing to notice is that these are always going to be n-1 dimensional, because all the vertices will like have their coordinates add up to the same thing. So it lives in like a hyperplane inside of Rn. Yeah, so yeah, and the vertices will be the permutations again. So we say a generalized permutahedron is a deformation of the permutahedron. And an alternative way to say this is that it's a polyhedron with its edge and ray directions of the form EI minus EJ, where these are standard basis vectors, EI and EJ. So it's not, I mean, it's not immediately obvious that those would be the same thing, but it turns out that they are. So Okay. So that's one family that I'll talk about. And so the work that I'm going to talk about in the seminar part of the talk is basically it takes some work that some other people, Dirksen and Fink, did for generalized permutahedra, and it generalizes this further to like a bigger family of polyhedra, which I'll say now. So to tell you what this is, I have to tell you about Coxeter combinatorics. So the idea here is that we notice that a lot of combinatorial objects that people like to study have a natural symmetric group action or are related to the symmetric group. So for example, the permutahedra from the previous slide were clearly related to the symmetric group because I obtained them by taking a point and taking its orbit under like the action of the symmetric group and taking the convex hull. And so in Coxeter combinatorics, we want to sort of generalize this to finite reflection groups other than the symmetric group. So what I mean by this is I'm going to, like, suppose I have some hyperplane arrangement in V, then I can create a group by taking the group that I get by all the possible ways to reflect things across the hyperplanes. And this, if I just take like some random hyperplanes, is not in general going to be like a finite group or a nice group, but there are certain special families of hyperplanes where this is a finite group, and these are these finite reflection groups that I want to work with. And so it turns out that there's a few infinite families of these, some of which I've listed on the slide here. And so for example, the one, well, okay, yeah. So then if I have a nice hyperplane arrangement like this, then I'm going to take the normal vectors of those hyperplanes and we call those roots. And then we call the pair of the vector space and the roots a root system. So for example, if my hyperplanes are all, for example, if I'm in R3 and my hyperplanes are x1 equals x2, x1 equals x3, and x2 equals x3, then reflecting across these is going to like switch two coordinates. So like reflecting across x1 equals x2 will switch coordinates 1 and 2 of my point. And so doing this in all possible ways gives me the symmetric group S3. And the normal vectors to these hyperplanes are going to be of the form EI minus EJ, where these are, so the normal vector to xi equals xj will be EI minus EJ. Where these are the differences of standard basis vectors. And so that one is what we call the type A root system. And that's the first thing that I've listed here. And that's going to be the one corresponding to the symmetric group. So you can see that this is kind of where the edge directions that I said generalized permutahedra have to have, they come into play here because they actually end up being the roots of the type A root system. So there's 3 other infinite families of these that I've listed here, although I probably shouldn't have separated B and C because they end up being the same hyperplane arrangement. They're just, the roots are different lengths. But so what I want to talk about in my talk is I'm going to be taking these different families of root systems and generalizing some results that hold for the type A root system and generalize permutahedra and the symmetric group, and like generalizing those to these other root systems. So for example, well, I guess I'll show you here. So Bn, you can see these normal vectors that I say are the roots. These are the normals to the hyperplanes. So you'll have like all the xi equals xj's. You'll also have xi equals minus xj for all I and j's. And then you'll also have the coordinate hyperplanes. And those will be your hyperplanes. So to generalize the idea of generalized permutahedra to this more general setting, we have some root system with these hyperplanes that give me a reflection group. And so what I'm going to do is I'm going to pick a point in my vector space that's not on any of the hyperplanes. And that's what I mean by a generic point. And then I reflect it over all the hyperplanes, and that gives me the vertices of some polytope. And I take the convex hull of that, and I call that the phi permutahedron, or the permutahedron for that root system. So for B2, for example, you can see like the hyperplanes would be these lines. You have like y equals x, y equals minus x, and then like x equals 0 and y equals 0. And when I reflect some point across all of those, I get this octagon. And then I also have the B3 permutahedron shown here. And so then when I take deformations of these, I get what I'm calling generalized Coxeter permutahedra. And equivalently, just like before, it has to have its edge and ray directions in the roots. So these are kind of that was like building up to like the polytopes that I'm going to talk about. So I think it's the end of the time for the pre-seminar, so I don't want to take up too much time, but yeah. Are there questions or?
So let's thanks Mariel again.
Thank you. I have a question. For the permutahedron, we picked like a specific point, like 1, 2, 3 to n. And here we're picking just any generic point. Is there like a best generic point to pick, like a maximally symmetric one or something?
So what I'll say is, like, for many purposes, it doesn't really matter, like, because you're just kind of looking at the, like, you care about having a polytope with a specified normal fan, I guess. So it doesn't matter exactly what polytope it is, but a choice that feels somewhat canonical is to take, so when you have a root system like this, you have these things called fundamental weights that go along with them. And so you can, which I'll allude to later, but I guess I don't really have a slide about them. But anyway, they come with a root system. And if you take the sum of all of them, then you get a point that satisfies this. And that, to me, that's like the nice thing to pick, I guess. But yeah, so.
Thank you.
I have a question. For the, is there like a quick way to explain for the valuation? You gave two definitions, the geometric and the algebraic, and there's a slight difference in them, but for this family, they're the two same thing. Is there any quick explanations about that?
I don't, yeah.
It's fine if there's no like.
There might be, but I'm not sure off the top of my head if I can give a good explanation for that. But I guess to be more clear though, they're not the same in general, but Alex Finks showed they were the same for generalized permutahedra. So I actually don't know if for the ones that I'm going to talk about, if they're the same. That's still open, I think, in the Coxeter setting. So that's why we do everything on the level of strong valuations, like this algebraic definition, which includes the other kind. Yeah. So.
Any other questions? Okay, so just thanks Mariel again, and